Well, good morning. My name is Michael Trick. I am chair of the judging panel for the Edelman competition. And welcome to this session, the third session of the Edelman finalists. Just a few announcements before we get going. First, the session is being recorded, person at the back, and so please turn off your cell phones so that we don't pick up your cell phone recordings. Please do not record or live stream this. You're welcome to take a few pictures along the way, but we're going to have a wonderful professional version of this available after the conference. Since it is being recorded, please try not to move around. If you do leave, then you won't be allowed back in, but there is a simulcast of this in another room. And finally, after the 40-minute presentation, there will be 10 minutes of questions from the judging panel only. I would now like to introduce LMI, Defense Logistics Agency.
Thank you. Good morning. My name is Jeff Bennett. I'm a Senior Vice President at LMI. And I want to introduce Dr. Tovi Bachman from LMI and Mr. Bob Carroll from the Office of the Secretary of Defense. About 6 years ago, Tovi came to me with a rather unique observation. He and his team had been analyzing 10 years of demand history, looking for ways to help DLA improve their forecasting for the 4 million spare part items that they manage. At the time, Bob Carroll was our DLA customer. He managed our contract. From previous work, we knew that about 3.5 million of these 4 million items had very little demand or, in most cases, no demand. The observation from Tovi was on the other 500,000 items, and what he found was very large demand variance for most of the items. Tovi told me that the best way for DLA to improve their forecasting was to stop forecasting. Yeah, I laughed too. That got my attention. It was contrary to every DoD policy and practice I'd grown up with over the last 40 years. But after 2 more years of research, Tovi was right. And while the wheels of government change often grind slowly, Tovi and Bob have a groundbreaking story to tell you today. The two entities that created Peak and NextGen were LMI and DLA. Today, we'll refer to the Defense Logistics Agency as DLA, and we'll refer to the Peak and NextGen solution as PNG. LMI is a 501c3 charity whose public purpose is to improve government management. LMI was created by the Defense Department in 1961 to solve DoD's most difficult logistics problems. We have no shareholders. We're a not-for-profit. Our focus is on providing our clients with solutions that truly meet their needs, not to our bottom line. Instead of a chart telling you about DLA, I have a short video from Jeff Curtis, the Executive Director of DLA's Logistics Support Directorate, who will introduce you to DLA.
So I work for the Defense Logistics Agency. We are America's combat logistics support agency. We provide full-scale logistics, everything from acquisition, storage, distribution, even reverse logistics for the United States military, the Army, the Navy, the Air Force, the Marines, some partner nations, armed forces, and other federal agencies. In a given year, we'll do about $40 billion worth of business, about $20 billion in fuel and energy, about $10 billion in medical, clothing and textile, and food. And then the other 8 or 10 billion will be in spare parts support. If we were a private sector company, we'd be ranked somewhere right around 55 or 60 in the Fortune 500. Our goal is to support the warfighter as efficiently as possible, but also to make sure he has what he needs when he needs it. We manage about 5 million different spare parts. Of those, maybe 100,000 have enough activity for us to forecast those and store those like a traditional retailer or wholesaler might. For the remainder, some of those are very critical, and we still have to have them for the customer whenever they need them. So finding the right level of inventory is key.
Thank you. Now let's talk about DLA's operating environment and what makes it challenging. Let's start with the customer side. DLA's customers, the operating environment is filled with uncertainty and unpredictability. Military operations are unpredictable due to wars, changes in operations tempo, budget turbulence, and changes in national priorities. All of this drives uncertainty in the maintenance programs and far too often results in substantial deviation or complete abandonment of what was planned. This, together with drifting failure patterns, makes for high demand uncertainty in DLA's customers' world and is thought by some to be not insignificant cost factor for DoD. Statistical demand forecasting performs poorly under this scenario. Collaborative customer demand planning also tends to fail because customers for DLA simply do not have better information far enough in advance of their need date so as to be actionable by DLA. Now let's look at DLA's supply side to see how they handle these highly unforecastable items. The difficulty isn't just so much in finding out what the right levels are and what the forecast is, but it's also finding somebody to supply or manufacture these high cost and small production run items. DLA's supplier base for many of these types of items is limited. The vendors simply bid on this work and work into their schedules based upon their needs and not necessarily the needs of DLA or its customers. As a result, lead times range from a few months to a few years. One obvious answer is to simply buy more responsiveness. And we tried this, but the cost was simply too high to sustain. So now let's talk about how these items with these attributes fit into DLA's overall item population. You heard earlier from Mr. Curtis that DLA manages about 5 million items. He also talked about the supply chains for fuel, medical supplies, food and subsistence, clothing and textiles, and spare parts. When we view the first of these in light of the second, we see that the spare parts represent about 4 million of these 5 million items, with the other supply chain sharing the balance. Spare parts are what we also call hardware items, nuts, bolts, screws, things that repair other things, will be the focus of today's discussion. Of these 4 million items, only about 1/3 of them have had a demand in the past year or so. Of these 1.4 million hardware items that are pictured here, we break them up into 3 segments. And you can see the segments as infrequent demand, those with highly variable demand, and finally those few items that have high demand frequency but low demand variability. And these are easily forecasted. The rest we found not so much. As we move from left to right on the chart, demand becomes more and more frequent, but we have fewer and fewer items responsible for that demand activity. Unlike many businesses that can simply choose not to support slow-moving items, DLA can't just get out of the business and leave its customers to fend for themselves. DLA and its customers are one. They're part of a greater whole. They're part of the Department of Defense. DLA cannot succeed if the department fails. As we move back from right to left, investment risk goes up. This is the risk that inventory will sit on the shelf for a long time. This is an opportunity cost. The risk to customer service also goes up as well as we move further to the left. Slow-moving items and uncertainty in the customer's environment often make it hard to identify and invest in those items that the customers will order versus those they won't. DLA has long recognized that slow-moving items on the left are unforecastable and hard to plan. There are about 1.1 million stock numbers in this segment. They were traditionally managed with a relatively simple set of business rules, as more complex forecasting techniques didn't work well for them. Performance for these items were typically low, and risk for these items was typically high. Items with more frequent demands, those in the 2 segments on the right, were forecasted using demand planning tools. But the performance and risk associated with these items was mixed. Some did well, some not so well. At some point, we finally recognized that some portion of this population, and a rather large portion as it turned out, had high demand variability where standard demand forecasting techniques did not work well for them. And so we segmented and identified those items that had high demand variability versus those that had low demand variability. The forecasting tools we're using didn't work well for the high demand variabilities. We realized that our definition of what was forecastable and what was not needed to change. We concluded that items were unforecastable not only because of infrequent demand, but also when they had high demand variability. And this was an important insight. But we still needed to develop inventory control methods appropriate to each of the two unforecastable segments. And for that, I'll turn it over to Toby Bachman.
Thank you, Bob. So now we're going to turn to the technical challenges in those two left-hand segments that Bob just talked about. First, infrequent demand. This is the case for peak. It's natural to start by trying to forecast lead time demands. But the problem is that most lead time intervals capture 0. That's the best forecast. But we still need to stock because of criticality. How do we decide when to order and how much? Now let's turn to the technical challenges for the frequent but highly variable demand. We start with frequent orders with highly variable demand sizes. There's lots of good information here. But when we look at most inventory control methods we see they throw away information at every step. First, there's a demand plan or forecast. Some of these use very sophisticated mathematical algorithms, but fundamentally they are averaging processes. And if you tell me that an average of 100 numbers is 57, I can come up with a huge number of possible sets of 100 numbers, all of which average to 57. So I've lost information. Then there's variance. Here, we're averaging square differences from the mean, a little more complicated, but still basically an averaging process. I can still come up with many different sets of numbers, all with the same variance and mean. I've still lost information. Next is fitting a demand distribution, whether it's normal, gamma, negative binomial, Poisson-Weibull, pick your favorite flavor. None of them fit well. In fact, we coined the term least worst fit to describe this. Many of the real demand distributions are multimodal, the many-humped camels we'd call it. More information is lost. Finally, order quantity, maybe an EOQ, maybe a quantity predicted to last a certain period of time is computed. But the amount ordered is based on the demand plan or forecast back at step 1, so it compounds the error. Now we're not just buying at the wrong time, we're not buying the right amount. So at every step, useful information has been lost, and this leads to stock levels, lead time demand plans, safety stock, and order quantity that are all too big or too small. And this leads to bad business outcomes, shortages for some items, excesses for others, and excessive buyer workload. So the current process loses information, but this gives us an opportunity for improvement. Now that we've seen the technical challenges, let's see what we do about them. There are 3 key elements involved in PNG. The first is portfolio management, targeting an entire population for business outcomes rather than individual items. This approach accepts the fact that some individual items will not have perfect outcomes. We simply aim to have more winners than losers. We avoid forecasting and distribution fitting, relying on empirical data to treat the demand uncertainty. When we use empirical probabilities, those are dynamically evolving over time. Finally, a 3-way trade-off between customer service, inventory, and procurement workload allow for a single integrated decision on population-level business metrics and sets inventory levels for each item. We do not ask the decision maker to consider separate investments in forecasted lead time demand, safety stock, and order quantities. So, those are the basic elements. Now let's start to look at the solution more closely. PNG offers decision makers a 3-way trade-off between customer service, value of inventory, and buyer workload. They pick the trade-off curve point that most closely aligns with their organizational objectives. So let's look at the trade-off curves. The horizontal axis is inventory value. The vertical is wait time to get an item. And the colors are different levels of buys awarded annually or workload. We start at the black star in the upper right. That's the baseline, the current operating point. We then consider options like the purple arrow, which pushes hard to reduce inventory value, with more modest improvements in customer service and reductions in buyer workload. The projected improvements are shown at left. We also consider choices like the one pointed to by the aqua arrow. This one pushes harder to improve customer service, reduce wait time, and reduce the number of buys annually, with more inventory than the one identified by the purple arrow, but still less inventory than the baseline. With that choice, we see a different set of improvements. But the hard part is getting to the trade-off curves. What does PNG actually do to get there? PNG is really a collection of two tools, Peak, which handles items with infrequent demand, and NextGen, which handles items with frequent but highly variable demand. So here's a high-level view. You feed in each item's demand transaction histories along with characteristics such as unit prices, lead times, and current assets. If fewer than 50% of quarterly buckets in an item's demand history have demand, the item goes to Peak. If 50% or more of the quarterly buckets in the demand history have demand, the item is assigned to NextGen. There's no need for an elaborate assignment logic based on classifying types of demand patterns. Frequency alone suffices, and it works well. I should note, going forward, we'll primarily work with a transactional demand. The quarterly here is just used for assignment logic. PNG produces a wide range of trade-off options, as we just saw. Once management selects where they want to be operating, PNG translates that decision to minimum maximum stock levels for every item. This is just a standard little s big S ordering doctrine. Now let's take a look at Peak. So here we have isolated demand spikes with unpredictable timing. The normal situation is no demand. That would be the winning forecast, but that's not helpful. So we aren't going to forecast. But we do know the largest or peak demand. So the basic idea is to protect against some percentage of that largest spike in case it should occur again, but in an affordable way. It's kind of like a surge protector for an electrical circuit. The normal voltage is a constant 12 volts, but sometimes there are voltage spikes. If the largest voltage spike is 50,000 volts, we might not be able to afford a surge protector that can protect against that, but maybe we can afford one that will protect against 10,000 volts. This may cover 90% of the spikes I see, but keep the protection affordable. Our normal no-demand situation is like the 12 volts, and the demands are like the voltage spikes. We want to protect against some affordable percentage of the largest spike in either case. So we make our minimum stock level equal to a price-based multiplier times the peak demand. We'll order when we get down to that. And to keep it affordable, we'll also use price-based order quantities. The max level is the min plus the order quantity. When assets get down to the min, we order up to the max. The hard question is, how do we get good values for multipliers and order quantities? Now let's dig a little deeper and answer that. We start with a population of items and sort them by unit price. We divide the population into 5 to 7 price groups based on price percentiles. We then determine each item's maximum quarterly demand, that's the peak demand. An item's min level is going to be a multiplier times its peak demand, and we will determine a price-based order quantity. Each item's multiplier and order quantity are still to be determined. Peak then generates thousands of possible multiplier and order quantity combinations for each price group. Those are called M's and Q's. We then run thousands of simulations with randomized demand spikes to see how each combination of M's and Q's would perform if the demand spikes occurred with different timing. This is based on random segments of transactional demand histories. From each simulation with a set of M's and Q's, we have customer service metrics, inventory value, and annual buys, a proxy for procurement workload. That feeds into a mixed integer program solver, which determines the best set of M's and Q's for many different trade-offs among customer service, inventory, and annual buys. We plot those trade-offs as a family of curves. Management picks an operating point that fits its goals, and that maps to the best sets in M's and Q's for those goals. And that gives us min-max stock levels for every item. We're done. So, what's unique and innovative about our Peak approach? Innovations in Peak include abandoning forecasting altogether. Instead, we build reorder points that protect against an affordable percentage of the largest demand spike. It's like a surge protector. Second, adopting a portfolio management approach, accepting some items will do better than others, but aiming for a high level of customer service at the population level without over-investing in inventory. It's essentially a hedging strategy, balancing the risks of too little and too much inventory. Third, stress testing stock levels from each set of model parameters against simulations using randomized segments of demand history. These simulations project customer service, inventory value, and buyer workload for each set of control knob settings. We consider thousands of parameter sets. Then, applying mixed integer programming to the outputs of thousands of simulations, finding the best set of model parameters for about 30 different trade-offs between key business metrics. Now, let's look at the other problem, frequent but highly variable demand. Real-world uncertainty is messy and involves unknown future human decisions. It doesn't conform to traditional probability distributions. Our goal was to build an objective function of min-max levels which would capture this messy kind of uncertainty, but still make the computation fast enough to be practical. There were many challenges along the way, and until the algorithm was built and fast enough to test in simulation experiments, we would not even know if it yielded any benefits. The process of building and testing was one of spiral development. Try something, go back, refine it, test again. We started with demand transactions and built 2 histograms for each item, one for demand inter-arrival times and one for demand sizes. It was challenging to build a cost objective function directly from these histograms, both mathematically and computationally, but an operations research paper by Shaheen pointed the way. Based on his work, we built probability distributions for inventory position and lead time demand directly from the histograms without distribution fitting and parameter estimation. A couple things became clear. The inventory state probabilities were highly non-uniform, unlike many traditional models, and the lead time demand probabilities were multimodal and ugly. Our hope was this would give us a more accurate portrayal of inventory position and lead time demands, and that this higher fidelity would lead to better outcomes, but we didn't know that yet. From these distributions, we built an objective function for trade-offs between key metrics for customer service, inventory value, and annual buys. By choosing different model parameters or control knob settings, we get different trade-offs. The population objective function is just the sum of the item objective functions. But although we could build the objective function, it was badly behaved, and it was unclear how to solve for min-max levels. We found a paper by Zheng and Federgren that had a fast search for min-max levels, but it was not formulated in terms of our observable data. And there were 3 conditions on the objective function for the search to work. It was unclear for a long time whether we could bridge the gap, reformulate our objective function in terms the search could use, and prove that our objective function satisfied the conditions. It took the better part of a year to find we could do this, a breakthrough at last. Now let's take a closer look at the inner workings of NextGen. So here's how it works in more detail. First, we build smooth histograms for order inter-arrival times and order sizes. We put more weight on recent observations. This allows us to adapt to changing demand over time. It took many experiments to tune these to adapt to evolving trends without overreacting to spikes. That was a hard step. From the histograms, we then build a function that gives the state probabilities for the inventory position for any candidate min-max. For example, if we input a min of 5 and a max of 10, it outputs the probabilities of the inventory position would be 5, 6, 7, 8, 9, or 10. And that distribution is highly non-uniform, unlike many current methods. It has higher fidelity. It's computationally challenging. There are many hurdles to overcome here. This capability to compute inventory position probabilities as a function of min-max levels will be used later in the search process. Next, we apply similar OR techniques to compute probabilities for different amounts of customer demand over a lead time, and that distribution is ugly. Here's a picture of a distribution for a real item. No textbook probabilities look like that. Again, we have higher fidelity. These do not depend on any min-max stock levels we consider, so we store this information for later use in the search. We now generate many sets, typically about 30, of model parameters or penalty factors to control trade-offs between annual buys, that's workload, inventory value, and backorders. These parameters are typically the same for every item in the population. For each set of penalty factors, we build a cost function. Function of candidate min-max levels. We use probabilities for the inventory position from 2A and for lead time demand from 2B to compute expected wait time, backorders, fill rates, and on-hand inventory value. A separate application of renewal theoretic techniques computes expected annual buys. We combine expected values for these metrics with penalty factors to build a particular objective function. We still haven't chosen those min-max levels. For each cost function, that is, for each desired metrics trade-off, we use an optimization algorithm based on the work of Zheng and Federgren to efficiently solve for each item's min-max levels. Each set of min-max levels is then fed to a simulation for stress testing against randomized segments of transactional demands. The simulation is completely independent of the next-gen math thus far. It doesn't believe in the next-gen math. It just says, how did you do? You can think of this step as stress testing against many possible futures for robustness of our solutions. The output of a simulation stress test is population metrics, wait time, inventory value, and annual buys. Management sees the simulation output displayed as a family of trade-off curves, just like peak. Picking a single operating point, just one decision, makes a simultaneous three-way trade-off between customer service, inventory, and annual buys. No separate decisions on safety stock, demand plan, or order quantity are needed. It's a single integrated decision with projected outcomes easily seen at once. The operating point selected maps to a set of min-max levels for every item. And now we're done. So, what was innovative about NextGen? First, developing a method of weighting observations and building histograms for demand sizes and arrival times so they continually evolve with the demand process but are sufficiently stable. They don't overreact to spikes. Next, using OR techniques in the literature to build a cost function directly from the histograms without distribution fitting and parameter estimation. This required a significant software engineering to develop techniques that were sufficiently fast to make the computation practical. Next, bridging the gap between our objective function built from observable data and the fast search algorithm formulated in abstract terms, proving that our reformulated objective functions satisfy the three conditions sufficient for the search to work. We also developed perturbation terms to modify the original cost function or to avoid overinvesting in just a few items or investing in items with large demand sizes at the expense of those with small demand sizes. And we proved this effective in simulation experiments. Lastly, rather than just accept metrics projections from next-gen optimization, we subject sets of next-gen stock levels to an independent simulation stress test against randomized demand segments, and use simulation output to plot the trade-off curves. This gives us more confidence that a chosen set of next-gen penalty factors will achieve the desired practical results. They've been tested against many possible futures that do not assume the next-gen math is reality. Now let's look back at how we got there. It was a long road, but there are some lessons learned from the journey worth sharing. So here's the project timeline. In 1999, we were looking at awaiting parts problems at Defense Department maintenance depots. About 40% of the stock numbers holding up repairs had infrequent demand. The best forecast was 0. You're almost never going to beat that. But if you don't stock, you can't serve the customer. So we decided that forecasting wasn't the answer. We had to start over with a blank sheet of paper. We asked ourselves, what could we do if we couldn't predict when or even if we would ever get demand on an item? And then it occurred to us that the normal situation for such items was no demand, that getting demand was a kind of aberration. And that led us to a risk management approach to protect against the risk that demand might occur. And this led to peak. In 2004, we showed the Navy would have had fewer aircraft down for lack of parts on 2 aircraft carriers had peak been used instead of the current policy. DLA had success using peak in its aviation supply chain during 2004-2005. But starting in 2005, DLA began an ERP implementation that shifted the agency's focus and priorities, and we were temporarily sidelined. Then, in the 2006-2007 timeframe, we looked at items with frequent but highly variable demand. This is that middle segment. Forecast errors were typically running in the range of 100 to 200%, no matter how sophisticated the forecasting. And no theoretical probability distributions for safety stock fit. In fact, all that we tried were rejected with less than 0.5% probability of false rejection. The math just didn't fit the data. Motivated by our success with infrequent demands, we created a new risk management-based approach. We had more data than for the infrequent demand case, so we looked at ways to use it, times between demands and demand sizes. 2 causal factors behind demand uncertainty, changeable maintenance programs, and uncertain failure patterns would be reflected in these data, if only implicitly. And this led to NextGen, which we developed and tested over the next several years. And in January 2013, PNG went live for DLA. Now Bob's going to talk about how DLA implemented PNG.
Thank you, Toby. Implementing Peak and NextGen took a coordinated effort across DLA. It involved IT services, planning, management, finance, stock positioning, and procurement. And it wasn't easy. First and foremost, it took leadership. And we're talking top leadership. Vice Admiral Harnacek, who was the former director of DLA, took a personal interest and got monthly progress reviews. He empowered a group of highly motivated people to make it happen, and he cleared obstacles for them. The best and brightest were brought in from the supply chains and given whatever they were needed. And these folks made Peak and NextGen work within our integrated process. There certainly are lessons to be learned in the implementation as well. Champions and change agents work to create a communication and communicate a strategic vision that was simple enough to be understood by all and yet detailed enough to convey the needed message. We did this with stories. We talked openly and honestly about what did and didn't work in the past and why. We invited questions and ideas, and we listened. We taught when the issue was lack of understanding on their part, and we learned and we changed when that was needed on our part. All cards were put on the table, and every effort was made to build a culture of trust and respect, and this was absolutely critical. The success of the project has received the attention of my new organization, the Office of Secretary of Defense. In the video you're about to see is the testimony from the Honorable Alan Estevez to the House Oversight Committee of Reform and on February 11th, 2015. Mr. Estevez is the Principal Deputy Undersecretary of Defense for Acquisition, Technology, and Logistics. That's a long and fancy title that means something to somebody, but probably means very little to you. To give you a better feel for who Mr. Estevez is, perhaps it's easier just to tell you that he is the deputy to the Honorable Frank Kindle. And Mr. Frank Kindle is a direct report to the Secretary of Defense, the Honorable Ashton Carter. In the video, you'll hear Mr. Estevez talk about DoD's implementation of a new forecasting methodology. Yet, didn't we just tell you over the past 30 minutes or so that this wasn't a forecasting technique? Put yourself in Mr. Estevez's shoes. How do you tell Congress that you're no longer forecasting the vast majority of the items you stock? How do you keep them from jumping to the conclusion that the only alternative to forecasting is unsupportable guesswork? He is merely explaining this in terms that most people are familiar with, and his message is one of outcomes achieved and not on the details of how this was done.
DoD manages over 5 million items valued at over $90 billion. Our actions to improve inventory performance while maintaining overarching focus of reducing risk to our warfighters have produced substantial results that have been acknowledged by GAO. For example, since 2010, DoD has been implementing our comprehensive inventory management improvement plan. Since 2012, we have reduced government-managed inventory by $14.4 billion, the first reduction in government inventory since the 90s. DoD is implementing a new forecasting methodology, which is producing improved material availability, decreased back orders, and reduced procurements.
As you just heard from Mr. Estevez, Peak and NextGen is making a real difference within DoD. After just 2 years, DLA saw considerable value in implementing Peak and NextGen for its most difficult items. Material availability went up at the same time as we had a $6 million reduction in excess inventory on hand, identifying the right items to dispose of and the right items to buy, a 35% reduction in annual buys, and a 70% reduction in canceled buys. Again, not buying and canceling and fluctuating with the demand patterns. This translated into about $127 million in labor savings. DLA is projecting that Peak and NextGen will bring about roughly $2 billion savings in working capital funds over the next 5 years. While it can be difficult to measure, one can easily see how improved availability increases readiness as we move to the right material, as we make the right material available when it is needed and in the quantities needed. We'd like to end with another video from Mr. Jeff Curtis. Here he explains the value that he saw from the implementation of Peak and NextGen at DLA.
The DLA director had asked that we look to save money for both the taxpayer and also our customer. So far, we're actually ahead of pace on this. I genuinely believe that Peak and NextGen has really helped us buy the right items, the right time, and the right amounts. That, coupled with a number of other efforts, I think we're genuinely doing more with less.
So that concludes our presentation, and we'd be glad to take any questions.